we're going to talk about some angle sum difference formulas for tangent. So angle sum difference formulas for tangent. So we did these for sine and cosine yesterday. We found formulas for sine of a plus b and cosine of a plus b and a minus b as well. And now we just want to do the same thing for the tangent function. It's not very hard to do. So here's what we do. We say to ourselves, okay, what is the tangent of x plus y? I want a formula for that. Well, I know that the tangent of anything is the sine of that thing over the cosine of that thing, right? Certainly that's true. The tangent of any angle, whether that angle is a single angle or the sum of two angles, whatever's inside the tangent function, tangent of that angle is the same thing as the sine of that angle over the cosine of that angle. And so now that we've written the expression in this way, we can sort of recognize, oh, well, sine of x plus y, we have a formula for that. It's the angle sum formula for sine. And cosine of x plus y, oh, we have a formula for that. It's the angle sum formula for cosine. So what I'll do now is just apply those two formulas. So what is the sine of x plus y? It would be the sine of x times the cosine of y plus the cosine of x times the sine of y. All right, and what is the formula for cosine of x plus y? Well, that is the cosine of x times the cosine of y minus the sine of x times the sine of y. Well, this is a formula then for a tangent of x plus y in terms of sine and cosine of x and y only. But it turns out that this can be cleaned up by quite a bit. Basically what we're going to do is we're going to do a trick. We are going to divide top and bottom of this whole fraction by the following expression. We're going to divide top and bottom by the following expression. Cosine of x times cosine of y, which is the expression that appears right here, by the way. And certainly you're allowed to divide the top and bottom of a fraction by whatever thing you want, right? I mean, that's what we do when we're reducing fractions. Like if you have, something like 12 over 9, and you say, oh, that's the same thing as 4/3, what you're really doing is you're dividing top and bottom by 3. So I can divide top and bottom of this fraction by whatever I want, and all I'm going to do is divide top and bottom by this whole expression right here. Now, if I'm going to divide this whole top of the fraction by this expression, then both of these terms need to get divided by that expression. Okay? Everything has to get divided by the cosine x, cosine y. So let's see what happens when I do that division. So here's the big fraction bar. I'm going to take this term here and divide by cosine x, cosine y. So that's sine of x, cosine y over cosine x, cosine y. And then I have a plus. I'm going to divide this term by cosine x, cosine y. So everything's getting hit over cosine x, cosine y. And same thing in the denominator of the big fraction, right? So I'm going to divide this thing by cosine x, cosine y. And finally, I'm going to divide this last term by cosine x, cosine y. So sine x, sine y over cosine x, cosine y. Okay. Now, why would you ever do this? This looks so much worse than the previous step. This is a terrible formula. But basically what you should notice is that a lot of nice things happen. So let's just take a look at each term. Here's my big fraction. Have a look at this first block. Okay? You probably noticed that the cosine y appears on the top and the bottom of the fraction. So this cosine y It cancels with that cosine y. But that just leaves you with sine of x over cosine x. Well, what's sine x over cosine x? That's tangent x. Ooh, okay. And then I have a plus. Look at this fraction. What do I have? Nothing cancels, but I do have cosine. Oh, wait, no, something does cancel. My bad. The cosine x here cancels with the cosine x there. And then I'm left with sine of y over cosine y, which is actually just tangent y. Cool. In this block, everything cancels, right? The numerator and denominator are exactly the same. Cosine x, cosine y, cosine x, cosine y. So the whole thing just becomes 1. And then finally, we have a minus. And here, nothing cancels. But if you notice, what I have is sine x over cosine x. That's tangent x. Times sine y over cosine y. That's tangent y. And this is the formula that I was looking for. Okay, so this is the formula for tangent of x plus y. That's the angle sum formula for tangent. It's pretty nice. Cool. So what I'd like to do now is just call your attention to the fact that the tangent angle difference formula is pretty much exactly the same. I won't derive this one because it's so similar to the derivation that we just did here. It's almost line for line exactly the same. So I'll just skip to the chase and give you the final results. The formula is very similar, except basically these two signs are flipped. Instead of a plus, you have a minus. Instead of a minus, you have a plus. So the tangent of x minus y will be tangent x minus tangent y over 1 plus tangent x times tangent y. So that's our formula for tangent x minus y. And like I said before, you don't have to memorize any of these formulas. You'll be given them. Just like for the sine and cosine, angle, sum, and difference formulas, these two formulas are so similar that we usually represent them with a single formula using plus and minus symbols. So let's go ahead and do that. So what would it be? Like, how can I represent these two formulas in a single formula? So here's what I'll do. I'll write tangent of x plus or minus y. So I'm sort of condensing both cases. Is going to be equal to what? Well, it's tangent x in both cases. That doesn't change. When it's a plus here, it's a plus here. And when it's a minus here, it's a minus here. So I write plus or minus, and then tangent y. And then I have a 1, so 1. Here, though, when there's a plus here, there's a minus here. And when there's a minus here, there's a plus here. So it's flipped. So instead of writing plus or minus, I'll write minus plus to indicate that the sign which appears here should be the opposite of the one which appears here. And then the last piece is just the tangent x times tangent y. So that is the formula that I'll give you, on a test, which encapsulates both of them, right? Okay, cool. So let's do a few examples. So let's do a few examples of this. So one thing that we can do is we can ask for things like, what is the tangent of 15 degrees, right? Well, the tangent of 15 degrees is not a unit circle angle. However, it can be written as the difference of two angles which are in the unit circle, right? It can be written as 60 minus 45, okay? And that is the tangent of a difference between two angles, and I just derived a formula for that. Basically, that's your x and that's your y. So I'm going to go ahead and use the formula. So I have a big fraction bar. So what do I have? I have tangent of x, so that's tangent of the first thing, so tangent of 60. And then since there's a minus here, I should have a minus here, so minus tangent 45. And then a 1, and then since there's a minus here, there should be a plus here. So plus tan 60, tan 45. Okay, great. Now, all we have to do is evaluate each of these expressions. So tangent 60, hopefully you remember that's either root 3 or root 3 over 3. This is going to be the bigger one. 60 degrees is more like this. The y value is larger than the x value, which means that the ratio y over x, which is what tangent is, should be sort of large, right? So that's going to be root 3 minus, hopefully you remember that tangent 45 is 1, and then I have 1 plus tangent 60, again, that's root 3, and then tangent 45, that's, again, 1, okay? So, so whatever this is, that's the tangent of 15 degrees, although it should be simplified. The only issue is that the denominator has a square root in it, and you're not supposed to have that for whatever reason. This expression is a little bit tricky to rationalize. So obviously there's root 3 times 1. The 1 isn't doing anything, so let me just get rid of that. It's just 1 plus root 3. As far as how you're supposed to get rid of the root in this denominator, the usual trick of multiplying top and bottom by whatever the root is doesn't work. If you multiply top and bottom by root 3, then you'll basically move the roots around. The trick is to use something that we did in the previous unit on trigonometric identities. You should multiply top and bottom by the conjugate of the denominator. Basically, the conjugate of a minus b is a plus b, and vice versa. So what I'll do is I'll multiply top and bottom of this entire fraction by 1. Instead of 1 plus root 3, I'll multiply top and bottom by 1 minus root 3. That's the conjugate of the denominator. And believe it or not, that will get rid of the root in the denominator. So let's see what happens. So I have, in the numerator, I just have to multiply everything out, right? Kind of a pain, but just do it. So root 3 times 1 is root 3. Root 3 times root 3, or actually it's root 3 times negative root 3. So that should just be minus 3. Negative 1 times 1 is minus 1, and then negative 1 times negative root 3 is plus root 3. Be careful with those signs. In the denominator, you can multiply everything out manually if you want. However, you can just recognize that this is going to be a difference of two squares because this is the product of a sum and a difference, right? It's a plus b times a minus b. That's the situation that multiplying by the conjugate is designed to create. So the expression after multiplying everything out, if you actually go through it, will be of the form a squared minus b squared. In other words, 1 squared minus root 3 squared. And as you can see, root 3 squared is just going to be 3. Multiply, if you didn't follow that, just multiply it out manually. You'll get to the same place. Don't worry about it. So what do we have in the numerator? The root 3 and the root 3 here combine to give me 2 root 3. And then the minus 3 minus 1 combined to give me minus 4. 1 squared is, of course, 1. Minus root 3 squared is just 3. So this gives me 2 root 3 minus 4 over 1 minus 3 is negative 2. It's looking pretty good, but actually we can go even further because this negative 2 can actually cancel into these two guys here. If you like, you can factor out a factor of 2 from the numerator. So that will become, let's see, so that will become, trying to keep the expression on the screen here. This last expression will be 2 quantity root 3 minus 2 over negative 2. And then you can say, oh, cancellation. So this 2 cancels with that one. The negative sign is still there, so it's a bit like root 3 minus 2 over negative 1. Dividing by negative 1 just flips the sign on each term. So that's going to be negative root 3 plus 2. Okay, so that's my final answer. Quite a bit of work to simplify that, but it's a good algebraic exercise. Okay, so let's do another example. Let's take a look at one of these. So let's simplify the expression tangent of 100 degrees plus tangent, plus tangent of 50 degrees all over 1 minus tangent of 100 times tangent of 50. How do you simplify something like this? This is just like some of the problems we did yesterday. It's kind of an identity in disguise. You might notice that this whole expression looks a lot like the expression that appears in the formula for the tangent sum and difference, right? So there's the formula, and then here's my expression. Very similar, right? Tangent of one thing plus tangent of another over 1 minus the product, right? Same thing here. Tangent of one thing plus tangent of another over 1 minus the product. So this expression is what you would get if you applied one of these formulas, either the plus or the minus, to some sum or difference. Now, is it the angle sum or the angle difference formula being applied? Well, because there's a plus here, when there's a plus here, that means that it's a plus in between. So it's actually an angle sum. So believe it or not, this is actually just a tangent of 100 plus 50. If you applied the angle sum formula to this expression, then you would get exactly this. Of course, that's just tangent of 150 degrees. What exactly is that? I'm not really sure. Off the top of my head, what I know is that that's like the pi over 6 angle sitting over here, right? It's like the small angle. It's like the 30-degree angle sitting over here. I know that the tangent of regular plain old 30 degrees, or pi over 6, is root 3 over 3. I know that. But of course, being in this quadrant, the tangent value is going to be negative. So the tangent of 150 has got to be negative root 3 over 3. Okay? Just one more thing I want to go over. I want to mention that in class, if you're not here, you're going to do. If you were in class, then you would do this with your group. But I don't want you to miss this derivation, so I do want to do it for you here. In class, what we'll be doing is we'll be deriving some so-called double angle formulas. This is basically things like, can we find a formula for sine of 2 theta, right? That's a double angle, twice the angle theta, right? I'll tell you right off the bat that it's definitely not 2 sine theta. Like, the 2 can't be pulled out. That's not what it is, unfortunately. The trick to finding the formula for this is to recognize that 2 theta can be rewritten as theta plus theta, right? I mean, that's the same thing as 2 theta. And then what you're looking at here is the sine of one thing plus another. We have a formula for that, right? The sine of A plus B is, I've already forgotten it. I always forget it after 30 seconds. It's sine of A cosine of B plus cosine of A times sine of B, right? So that's the formula. Now, we can use that. It's just that A and B are both the same thing. They're just both theta. So we find, therefore, that sine of theta plus theta, which is what sine 2 theta is, must be sine of theta times cosine of theta plus cosine of theta times sine of theta, right? Now, what you might notice is that these two terms are actually the same. I mean, the factors are reordered, sine, cosine versus cosine, sine. But otherwise, they're identical. So they're like terms and can be combined, and you just get 2 copies of sine theta, cosine theta. And so that's the so-called double angle formula for sine. And basically, double angle formulas can be obtained for cosine as well. For cosine, it's a bit strange because there are multiple ways of writing it. And in class, we derive all of these, but I just want to make sure that you don't miss them. So try to do the derivation yourself. But cosine 2 theta, one way of writing it is cosine squared theta minus sine squared theta. That's one version of the formula. This is not very good. As you'll sort of see, we don't really use this version of the formula very often because it involves 2 trig functions. Another way of writing this, basically if you replace the cosine squared with 1 minus sine squared, then you'll get the following version. You'll get 1 minus 2 sine squared theta. This is a good formula because it only involves a sine. And on the other hand, if you take this sine squared and replace the sine squared with 1 minus cosine squared, then you'll wind up with 2 cosine squared theta minus 1. So those are the three. So cosine 2 theta kind of has three different versions, and which formula we use is really just dependent upon what's convenient, what information we have available to us. So, okay, yeah, so that's it.